So first off, what are polynomials? They are functions in this form right over here. F of x equal to a of n. The subscript n, you don't really have to care about that. It's mainly just this exponent over here. So a of n x to the power of n plus a of n minus 1 times x to the power of n minus 1, so forth, all the way until a of 0. This being the last term. Where n must be greater than or equal to 0, and n must be an integer. So basically, n cannot be any fraction, it cannot be any negative number, and it cannot be a decimal. And something to note here, a of 0, there is technically an x here, so this would be the entire term. But remember, any number to the power of 0 is just equal to 1. So this, a of 0, x to the power of 0, this is just equal to a of 0 times 1. And we don't really ever write the 1 here, so that's why it's just written as a of 0. Now, moving on. So these are some definitions of terms that you must know for polynomials. So the lead term. The lead term of a polynomial is a term with the highest degree or power. So we have this polynomial over here, 2 times x to the power of 5 plus 4 times x squared minus 3x minus 10. So the exponent for this one is 5, exponent here is 2, this one's 1, and this one's 0. And of course, 5 is the greatest out of all 4. So this is the leading term. And please note the term is the entire thing here. Okay, so it's 2x to the power of 5. It's not just the variable itself. Okay, now lead coefficient. So to find the leading coefficient, you must first find the leading term. So we have the same sample here. And we already know what the leading term is. It's 2 times x to the power of 5. So the lead coefficient is the number attached to the variable. Okay, so let me rewrite the term here, 2 times x to the power of 5. The variable is here, that's this component. This is the coefficient. So the coefficient is always the number, the numeral part of the term. And the constant term is the term with degree 0, which is just the last term. So once again, same example. This would be the constant term because technically this is really negative 10 times x to the power of 0, where written in this form, right, a of 0 is just the negative 10, and of course the x to the power of 0 is just the x to the power of 0. And remember, as I said earlier, x to the power of 0 is equal to 1, so this would just be negative 10 times 1. And so always remember that the constant term is just a term where the x is not written. Okay, any questions here? Okay, moving on. So I'll be talking about the Cauchy's bound. So the Cauchy's bound is a method used to define an interval of possible real zeros. And if you're unfamiliar with what zeros are, if we have a graph, doesn't really matter what the graph is, and we have, let's just go with this graph, okay? these zeros are just these points here. Okay, so it's just these points here on the x-axis. These are the zeros, and a polynomial can be written as x minus and then whatever the zero is times x minus the other zero and so on and so forth. Just in case you forgot what the zeros of a polynomial are. So we are given this this polynomial, and please know here that the degree n, so this for this term, the degree has to be greater than or equal to 1. Okay, so you cannot have some polynomial that's just f of x is equal to a of 0. There's no, like, this thing does not apply. Cauchy's bound does not apply if it's just a of 0. There has to be an a of 1, x of 1, plus a of 0. This is the minimum. So, and in order for this to actually be clear, we have to use this example here. So it's same polynomial as before, 2 times x to the power 5 plus 4x squared minus 3x minus 10. So basically, Cauchy's bound only uses the coefficients. So it only uses the 2 here, the 4, the -3, and the -10. This is all you need for Cauchy's bound. So a of 5, which is the coefficient for this term over here, so the leading term, is equal to 2. A of 2, which is the coefficient for this term, is equal to 4. A of 1, which is the coefficient for this term over here, is -3. And then the coefficient for this term is, well, it is the constant, so it's just -10. And basically, what Cauchy's bound states is all the numbers of, so basically the coefficients of all the numbers of all the terms except for the leading term divided by the leading term is all you need. So we have a of 0, right? So this is the constant divided by the leading coefficient. This is the second terms. So this is basically a second last term's coefficient divided by the leading coefficient, and so on and so forth. So we know that a of 5 is the leading coefficient. So Cauchy's bound to rewrite this. You basically just write a of 2 over a of 5. Okay, remember it is the absolute value of it. So basically, absolute value is just, doesn't matter what the number is, it has to be the positive version of it. So the absolute value of 10 would just be 10. Or sorry, the absolute value of -10 is 10, and the absolute value of +10 is still 10. Okay, that's all what the absolute value is. And so the next one would be a of 1 over a of 5. And the third one is a of 0 over a of 5. And so to rewrite this one, we have a of 2 is 4. It's 4 over 2. And the absolute value of this is just 2. A of 1 over a of 5. A of 1 is -3. So -3 over 2. Remember, it's the absolute value, so it doesn't matter if this is positive or negative. You write the answer as a positive. So this is 1.5, positive 1.5. And then a of 0 divided by a of 5. A of 0 is -10 divided by 2. The absolute value of this. So once again, it's -10, but you may just make it positive regardless. So this is equal to 5. And so Cauchy's bound states that if m is the largest of these numbers, so basically we have 2, we have 1.5, and we have 5. M is the largest of these, so that, and 5 is the largest, so M must be equal to 5. And it states that the zeros must lie in this interval here. So that's negative M already said is equal to 5. So this is the negative of 5 plus 1 and 5 plus 1, which comes out to be -6 and 6. So this is the interval of which the zeros can lie in, and it's -6 to 6 inclusive. So basically, now you know that the the intervals must be -6. It can be -6. It can be -2. It can be negative pi. It can be 3. It could be any number, but it has to be in between -6 and 6 inclusive. Any questions here? Okay, then moving on. So now moving on to rational roots theorem. So in a polynomial, so once again, same thing, a of n times x to the power of n plus a of n minus 1 times x to the power of n minus 1, so forth, all the way until a of 0. This part you don't really have to mind. All rational roots of the polynomial must be of the polynomial plus or minus p over q must have p divides a of 0. So this top part must divide into a of 0, and the q, which is the denominator, must divide into the leading coefficient. So basically, to make this clear, we have this over here. Remember the rational roots. So it is in the form of plus or minus p over q. The p must divide into the -10, and the q must divide into the 2, so the leading coefficient. So basically, the way you can write this is so p is the -10 here, and then the q is the 2 here. So remember, this is the plus or minus, and -10 divided by 2 is just -5. So since it is a plus or minus, you can just write this as plus or minus 5. Okay, so this is a possible root. Or sorry, I made a mistake here. The q, okay, the q can be any of the factors, of the factors of these two terms. My mistake. So this is still one of the possible ones, right? So we have p. Remember, p must be the factors of -10. Or since it doesn't matter if it's negative or not, you can just find the factors of 10, right? So that's 1, 2, 5, and 10, right? 1 times 10 is 10, and 2 times 5 is 10. And then we have Q is the factors of 2, and 2 is a prime number, so it's just 1 and 2. And basically, you just take all of these and you divide them by all of these, okay, separately. So given that it is plus or minus P over Q, you can write this as, let's start off with Q equaling to 1. So it can be plus or minus 1 over 1. It can be plus or minus 2 over 1, plus or minus 5 over 1, and plus or minus 10 over 1. And then when Q is equal to 2, it can be plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 5 over 2, and plus or minus 10 over 2. And you can simplify all these, right? Plus or minus, so that's plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 0.5. This is 2 divided by 2 is just 1, and you already put 1 over here, so you don't have to rewrite it. 5 over 2 is plus or minus 2.5, and then 10 divided by 2 is just 5. You already wrote 5 over here, and you don't need to repeat. So basically, these are all of the possible rational roots. These, like, not all of them have to work, right? Not all of them have to work, but some of them might. So basically, 1 could be a root, 2 could be a root. And remember, it is a plus or minus, so it can be the positive or negative of 1, positive or negative of 2, positive, negative, or 5, and so on. Are there any questions here? Okay, then move on. So now we have the Vietta's formula for higher degree polynomials. So, and this is something to note here. This is higher degree polynomials. So it wouldn't make sense for you to use the Vietta's formula for a polynomial, let's just say f of x is equal to x squared plus, I guess you could do x minus 2, right? This is just degree of 2. So you wouldn't really use Vietta's formula. You only use Vietta's formula for high degree ones. So basically, polynomials with multiple terms, let's just say x to the power 5 plus x to the power 4 plus x to the power 3, and so on. So basically, we are given, once again, this is just a form of a polynomial. And this time, please note that it is just rewriting this a of n minus 1 times this dot 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 all the way until plus a of 0. This has to equal to 0. Okay, so the polynomial must equal to 0 for Vietta's formula to actually work. Okay, and we assume that there are roots R1, R2, R3, all the way until Rn. So basically, if we have a polynomial, let's just say x of 5 plus x of 4 plus x of 3 plus x of 2 plus x of 1. There are roots of R1, R2, R3, R4, and R5. So basically there are 5 roots. The number of roots is equal to the number of, or is equal to the highest degree. So basically the degree of the leading term. And with this, we have this. So let's just take this one. So we have the sum of all of the terms. So we have R of 1 plus R of 2 plus R of 3 all the way until R of n. So we can write this using this example. R of 1 plus R of 2 plus R of 3 plus R of 4 plus R of 5 should be equal to the negative, okay, the negative here, of A of n minus 1 over A of n. So basically is the leading so in this case, it would be A of 4 over A of 5 because this is A of n minus 1. N in this case is equal to 5 because 5 is the leading term. It is the highest degree. And then the numerator is the term right before, or sorry, right after. So the next term is x of 4, right? 5 minus 1 is 4, so it'd be the coefficient of this one. So in this case, the sum of all of these, A of 4 is just 1, right? The coefficients of these two are just 1, so it'd just be 1 over 1, which is equal to 1. Now we have the next one. So this is not as often used because of how difficult, because of the number of terms in it. So are there any questions for this first one? Because I'm gonna have to clear.
I think we're good, Fred.
Okay, then let's talk about this one. So let's actually use the polynomial from before, right? F of x is equal to, what was it? 2x to 5 plus, okay, I'm forgetting, what is it? 4x squared minus 3x minus 10. Okay. So 4x squared minus 5x minus 10. Okay, so we're just going to be reusing this polynomial. And so basically, the sum of all products of two terms is just A of n, so A of n minus 2 over A of n. So it is the leading coefficient as the denominator, and the next term, actually, I'm going to change this just so it can suit our example. Let's make this 4x of 3. Okay, so using this example, right, we should have five of these of the roots. So R1, we have R2, R3, R4, and we have R5. And basically, this is saying this sum of all products. So we have R of 1 times R of 2 plus R of 1 times R of 3 plus R1 times R4 plus R1 times R5. And then you're also going to have to continue on to the next one. So R of 2 times R of 3 plus R of 2 times R of 4 and so on. Actually, I'll just write it out. R of 2 times R of 5. And you repeat with 3. So it'd be R of 3 times R of 4 plus R of 3 times R of 5. And then finally, R of 4 times R of 5. And basically, let's write it. Basically, this equals to negative a of n minus 2. So in this case, n is 5, right? That's the leading terms degree. Minus 2, so 5 minus 2 is 3. That's why we wrote this as 3. So this would be a of 5 minus 2 over a of 5, which is the, sorry, no negative. Okay. This is a of 3 over a of 5, and a of 3 is just this coefficient over here, so that's 4. This just becomes 4 over a of 5, so the leading coefficient, which is 2. And so you basically have that all of these, so the product of all of these added together is equal to 2. And then this next one here is the same thing, except it's the sum of all products. So, well, I'll just write it over here. So that's R of 1 times R of 2 times R of 3 plus, so still using this example, this would be R of 1 times R of 2 times R of 4 plus R of 1 times R of 2 times R of 5. And then you're basically just repeating over and over and over again, all the way until the last one would be plus R of 3, R times R4 times R of 5. Okay, and this is equal to the negative. This is equal to the negative of, remember, n is 5 in this example, so you have 5 minus 3 over a of 5. This is equal to the negative of a of 2 over a of 5. We don't have an a of 2 here, so in this case, this would not really work out. Okay, but like these, so like for these two that I just went over, they are not used often because of how tedious they are. Now let's actually do this last one. So the product of all n terms. So in this case, it's just the product of all of these. So R1 times R2 times R3 times R4 times R5. And this must be equal to negative 1 to the power of n. So in this case, that's 5. And that times the constant, so a of 0 over the leading coefficient. So in this case, a of 5. And this is negative 1 times itself 5 times. Because this is an odd number, that means that this just turns out to be a negative 1. And this times a of 0 is negative 10 divided by the leading coefficient, which is 2. These two negatives cancel out, so this just becomes, so the product of all of these roots is equal to 5, using this example here. And please remember this -1 to the power of n. Okay, that is very important. If and so if, let's just say in this example, I changed it. So I added, let's just make the 6 instead. Okay, if the exponent of this one was 6, then there would be r of 6. That mean that this would be 6. And so the -1 would, -1 to the power of 6 is equal to +1. Okay, so this negative sign can alternate between negative and positive, depending on the number of, depending on the degree of the leading term. Are there any questions here? Okay,
No.
in that case, I would like you guys to try out this over here. Okay, this math context question. So the polynomial of x cubed minus a of a times x squared plus bx minus 2010 has 3 positive integer roots. What is the smallest possible value of a? Okay, and big hint over here, use Vietta's formula. Okay, use Vietta's formula for this. I'll give you guys 3 minutes to do this. Okay, the 3 minutes is up. You guys how to do this. Basically, we have so we have this polynomial over here, um, and we have so if these coefficients. So a of 3 is equal to 1. That's the leading coefficient. A of 2 is equal to negative a, and a of 1 is equal to b, and then a of 0, which is the constant, is equal to negative 2010. And we are using the product rule. We will be using the product rule. So we have 3 roots, right? Because the leading term's degree is 3. So we have R1, R2, and R3. And this is equal to negative 1 to the power of n. N is the 3 here, so this is 3 times a of 0 over a of 3. Because a of 3 is the leading constant, or sorry, leading coefficient. And negative 1 to the power of 3 is still negative 1 because 3 is an odd number. And a of 0 is the negative 2010. And a of 3 is over here, 1. And the negatives cancel. So this turns out to be 2010. Okay, so the roots of this polynomial multiplied together is equal to 2010. Okay, and so we need to find the smallest possible value of a. And the way we do that is, we still need to find another one. So the other easy one to figure out is R1 plus R2 plus R3. And this is equal to a of the negative of a of n minus 1. A of n, remember, is 3. So 3 minus 1 over a of 3. This is equal to the negative of, so 3 minus 1 is 2. So we have this here. So this is equal to negative a. So the negative of negative a over the leading coefficient, which is 1. And the negatives cancel out again, so we have a. So we have the sum of all the roots is equal to a, and we have the product of all the roots is equal to 2010. And so in order to get the minimum value of a, we want to find the prime factorization of 2010, because that will that will give us all of the possible factors of 2010. So that'll give us all the possible values of R1, R2, and R3. And I'll write it here. So 2010, you can divide it by 2, right? So we have 2 here. Once this is divided by 2, actually, I'll write it in a different way. So 2010, we have 2. What does this become? This becomes, so 2010 divided by 2, that is 1005. And of course, and since this ends with a 5, you automatically know this is divisible by 5, which is another prime number. And then this splits into, so 1005 divided by 5, that is 201. And in 201, 2 plus 1 is equal to 3. And the the divisibility rule for 3 is the sum of the digits has to be divisible by 3, and 3 is divisible by 3, so automatically know 3 is another prime factor of 2010. And this divides into 67. And 67 is another prime number. So we have 2010 is equal to 2 times 3 times 5 times 67. Okay, but this is 4 prime numbers. This is 4 numbers, and we only want 3. So now we need to find a way to make it so we get the 3 small. So we get 3 numbers, 3 factors of 2010. That is the smallest. That has the smallest possible sum. Because we already know R1 plus R2 plus R3, which is the 3 roots, is equal to A. And so we need A to be the smallest it can possibly be. So we can, logically thinking, right, you would multiply the 2 and 3 together, right? You would not multiply 5 and 67 because that gives a huge number, and that will obviously not be the answer. So we have 2, 3, or 5, right? We need to multiply one of these 3, one of the 2 of these 3 together. So we can first try out 2 times 3. What is that? That is 6. Okay. What is 2 times 5? That is 10. Okay. And 3 times 5, that is 15. All right, so then let's test it out. Right, let's first test out the 3, the 2 times 3, which is equal to 6. So in that case, the factors would be the roots would be 6, 5, and 67. And what do these add up together? When you add these together, you get 78. Plus together is 78. Now let's test out the 10. Right, so now we have 3 plus 10 plus 67. This is equal to 80. And then let's test out the last one, which is 3 times 5, which is 15. So we have 2 plus 15 plus 67. This is obviously larger, but just to put what the sum is, it is 84. So of course, this one is the smallest one. And so that means that the factors must be 6, 5, and 67. So the answer is A here, 78. Are there any questions?
No.
No. Okay. Then let's try out this next math contest problem. This is also for the Vieta's formula. Okay, and something to note here, Vieta's formula is very useful. That is why I'm using multiple math problems to explain Vieta's formula. So over here we have all the roots of the polynomial z to the power 6 minus 10 times z to the power 5 plus a times z to the power 4 plus bz times z cubed plus c times z squared plus dz plus 16 are positive integers, possibly repeated. What is the value of b? Okay, you have to know here, possibly repeated, right? So this is hinting at you that there are repeated numbers for roots. Okay, so to get you guys started off, right, this is 6 here. It's slightly blurry. This is 6. So we have six roots. We have R1, R2, R3, R4, R5, and R6. So you would use the sum. Uh, you would find the sum of these, and you'd also find the product of all the six roots, and then from there, you can find the answer. Okay, I'll give you guys 3 minutes again to do this problem. Okay. 3 minutes should be up. There. Okay, so we have the 6 roots. And we have this here, so the sum of all the roots is equal to the negative of -10/1. Let me write this out actually. A of 6 is equal to 1. A of 5 is equal to -10. A of 4 is equal to A. A of 3 is equal to B. A of 2 is equal to C. A of 1 is equal to D. And A of 0, which is constant, is 16. So over here, n is 6. 6 minus 1 is 5. We're just using this one divided by the leading coefficient. Remember, it's the negative of it. So negative of the -10 divided by 1, that's the negatives cancel, so we get 10. And then we're trying to find the product. So R1 times R2 all the way until R6 is equal to -1 to the power of the highest degree in the polynomial. Remember, n is 6 because that is the degree of the leading term. And -1 to the power 6, since 6 is an even number, this just becomes +1. And we have 16 divided by 1, so this becomes 16. Now, something to know here, right? You have positive integers and we have possibly repeated, right? We have positive integers, we have possibly repeated. And since we know that they are possibly repeated, right? We have multiple roots and the product is like a small number. We have the sum of all the roots and it is a small number. It is 10. And so because we know that it is positive integers, we know that they must, that means all of them are positive integers. And hopefully you can realize that 16 is equal to 2 times to the power 4, right? 2 times 2 times 2 times 2 is equal to 16. And so this also requires that thought process in order for you to get the answer, right? So because 16 is equal to 2 to the power 4, we can try out 1, since we already have 4 2's, right? We can just add 2 more 1's, because 1 times 1 is just 1. 1 times anything is just itself. And so we can test this out, right? 1 times 1 times, that's 4 2's. And so this is equal to 16, right? So this works out for the product. Now we can try 1 plus 1 plus 2 plus 2 plus 2 plus 2. 4 2's, that's 8. 1 plus 1, that's 2. 2 plus 8 is equal to 10. Perfect, right? Now, so we can see that 2 1's and 4 2's works out for these two, for the two values that we got here. And so we're trying to find the value of B. And so moving down. Sorry. Okay. So now, since it is all positive integers, we know that all these are positive. And like I said earlier about the zeros, these are all the zeros. Okay, these are the roots. Roots and zeros mean the same thing when it comes to polynomials. So we have this, well, I'll just call this f of x. So now we have f of x is equal to x minus 1 squared, since we have two of them. And then we have x minus 2 to the power 4, since we have since we know that this root comes up 4 times. And so we can expand this. So this becomes x squared minus 2x plus 1. And then this one, now I'm going to erase this part. Is there any questions up till now? Okay,
No.
I will erase this part. Okay, there you go. So this is equal to all this. Oh yes, and I changed it to x. You can use x or z or a, doesn't matter, because x is just a variable, it's just a placeholder. So this is okay. This is equal to negative. You know what? I'm going to rewrite this so that I have more space. This is equal to x squared minus 2x plus 1 times x to the power 4 minus 8x cubed plus 24x squared minus 32x and then plus 16. Okay, and we know that so b is, remember the term b, it was a plus b times, well, now I should use x, bx cubed, right? So we only want, so from this, right, we only want what will multiply to x cubed, right? Because we are using the distributive property, right? So if we were to write all of this out, it would be x squared times x to the power 4 plus x squared times negative 8 times x cubed, and so on and so forth. And so we only want the ones that multiply to x cubed. And so we would have, so let's first look at x squared. X squared times negative 32x will give us an x cubed. So we take that. X squared and negative 32x plus, now we have negative 2x. If we multiply that by 24x squared, that gives us an x cubed. So we take that. So that's negative 2x times 24x squared. And we have the 1 here. 1 times the negative 8x cubed will give us another x cubed. So you plus the 1 times negative 8x cubed. And now we're left with a negative 32x cubed. This is minus multiplied by positive, still negative, so minus 48x cubed. And then this is once again still negative, so minus x or 8x cubed. And now once we do this, we just get negative 88x cubed. And we can see here, we have b z cubed. I just wrote this as an x. And see x cubed, right? We're looking at the exponent cubed. That means that b must be equal to negative 88 because that is because the two terms correlate with each other. So our answer is A, negative 88. I guess class, I went a little bit over time. I guess that is the end. Any questions for this problem?
I think good.
Okay, and I'll stop sharing.